Okay, let's do another video here on logarithms. I'm calling this the properties of logarithms part 2. Okay, this is dealing with section 6.5 in John Grimma's stuff. Okay, so that part of the homework. This first part here, I just want to reiterate what we did last time here. If x and y are positive numbers here, positive real numbers, we had the following properties we showed holds. Logarithm base b of xy is the logarithm base b of x plus the logarithm base b of y. The logarithm base b of the quotient x over y is the logarithm base b of x minus the logarithm base b of y. The logarithm base b of the exponential x to the r, where r is any real number, can be written this way. It's equal to what? R times the logarithm base b of x. So we were saying you can actually bring that exponent r on the outside, and this is multiplication here, right? Okay, let's use some of these properties in some of the questions in section 6.5 here. Here he starts us out here. He says, write the expression in terms logarithm base b of x, logarithm base b of y, logarithm base b of z, where b is whatever base is actually involved in the problem. Okay, for example, number 14 here, you've got the logarithm base b of x times y cubed times z to the fifth, right? There's implicitly times in there, right? Okay, logarithm of a product is fundamentally what this is first, okay? So you could do this. I'm going to use this. By the way, you can use induction on this. If I have a problem x, y, z, I would add what? The logarithm base b of z here. That's easy to see here. So what I'm going to do here, this is the logarithm base 4 of x, right? And because that's times, this becomes the logarithm base 4 of the next factor in this product on the inside. That's y cubed. And then plus the logarithm base 4 of z to the fifth power. I guess I can squeeze that in there like that. Okay, does that make sense? Okay, I'm not done yet. I haven't written everything in terms of just log x, log y, and log z yet, have I? Okay, I need to do a little bit more work. This one's acceptable. That's the logarithm base b. b is 4 in this case. It's a logarithm base 4 of x. That's cool. Logarithm base 4 of y cubed. How can I write this strictly in terms of the logarithm base 4 of y? Well, I'm going to use this third property here. We were calling that the exponential rule, actually, previously. I can bring what? The exponent. If I'm taking the logarithm of an exponential, I can take the exponent out front as a multiplier, right? Okay, so I'm going to do that right here. I'm going to take that 3 up front. That's log base 4 of y. By the way, if you want to drop these parentheses here when you're doing this, you can do so. How about this? The 5, for the 5 would come out by the same reasoning. Okay? Okay, so the point is, the only thing we're taking logarithms of here in the end are what? Logarithms with respect to x, y, and z. Or of x, y, and z. So this is what we want for our final answer. Okay? So box in your final answer there. Let's try a few more of these. Okay, let's look at 16. Well, the first thing you see is this is fundamentally a quotient. So I'm taking the logarithm of a quotient. Okay, do you remember our quotient rule here? I've written as number 2 here. The logarithm base b of a quotient is what? The difference of the logarithms. So it's going to be the logarithm base b of x to the 4th minus the logarithm base b of y. Okay, this still isn't acceptable, but this is. What do I want to get rid of here? Yes, the 4th power. I want to put that out front as a multiplier. So it's 4 times the logarithm base b of x minus the logarithm base b of y. I'm going to write it without the parentheses this time, just because you can. Okay, I could have done that over here. Okay, just so long as you're not mixed up here. Okay, this is a single quantity, that's a single quantity. Alrighty, how about this one? logarithm base 7 of x over 7z cubed. That'll be the logarithm base 7 of x. Once again, because it's a quotient, the logarithm base 7 of yz cubed, like that. Okay, now this is a what? That's a product and you remember, if you're taking the logarithm of a product, you can break it into what? The sum of logarithms, right? Oops. By the way, you can skip steps if you get good at this, which was what I almost did. Now, what's wrong with what I have written here? There's something missing. Yeah, you probably noticed here, there should be a minus sign on that, right? Because I'm actually breaking down this whole logarithm of this product here into a sum. That's okay, but I would have to need what? I would need parentheses, or in this case I'll write square brackets, right, to set that off there. So that negative sign actually distributes through this stuff. So let's go ahead and write this: logarithm base 7 of x minus logarithm base 7 of y minus 3 logarithm base 7, I forgot the 7 there, of z. Notice I also jumped in there and did what? I brought the 3, the third power, out front as a multiplier using our exponential property. Okay, so I'm just using these 3. Right? All right, so there it is. The only logarithms left are logarithms of x, logarithms of y, logarithms of z. If I knew what those values were, I could plug them in here and find the logarithm of the original expression here. How about this one? The only difference between this and the previous ones basically is I'm throwing in here some radicals, or he is throwing in some radicals. Okay, so let's maybe, before we do anything else, let's write these with exponents, right? You can always write without radicals if you're willing to use rational exponents, right? Okay, so this is actually x to the half power. This is y to the, what, 1/3 power. Okay, now I'm going to break this down like I always do. This is the logarithm of a quotient, so that's a difference of the logarithms here. This is one of the few times that I write my fractions with a slash mark, is when they're exponents. You might notice. Am I done yet? No, I'm still taking logarithms of something other than just x or y. Right, I have a little more work to do. What am I going to do now? Move the half out front as a multiplier, as a factor on this. And my 1/3, I'll pull that out there in front also. And we've got our final answer, because now all I'm doing is taking logarithms of x and y. In this case, to the base b is 5. Okay? Alrighty. Now I threw an extra one in here. Okay, so this is not in John Grimm's, but I'm going to put it in here. Okay, because I'm probably going to give you one like this. It's logarithm base what, everybody? Logarithm base, well, if there's no base written, the base is implicitly 10. Yes, that's common logarithm. Okay, so here's what you're going to do. It's going to be logarithm base 10. You could actually put the subscript 10 down there if you wanted, but I'm not going to. Okay, and I'm going to jump right in there. I hope you guys see what I'm doing here. And since this is downstairs, do you see that? You see how quickly you can jump from here to here, right? After you get used to this. Write out the details here and see how you can jump from here to here. When you get good at this stuff, right? You can write the answer. I know it's a negative in front here because it's down in the denominator, right? Down in the denominator, I knew there were negatives in front. Okay? Positives up in the, numerator, if the powers are positive also. But one last thing here. What's the logarithm base 10 of 100? What power do I have to raise 10 to get 100? Second power, right? 10 squared is 100. Okay? So this should actually be for your final answer. If you circled that, you would only get partial credit because you didn't simplify it enough for me. Okay? I'm going to write it without parentheses again this time, just for a change of pace. Okay? There's what we would want for our final answer here. Okay? In this particular problem. Right, I hope this makes sense to you. We're going to be going the other direction in these next problems. So you're going to have problems very much like this. Write as a single logarithm, and you only want to use positive exponents. Okay, so he's asking you to go in the reverse direction from what we were just going. Okay, so like in this problem, you'd be going from something that looks like this as your beginning, and your end would want to look like this. Logarithm of something. Okay? All right, so we're inverting what we just did. We're going the opposite way. Okay, let's do this. First question for you. This is ln. What's the base? Yes, the base is e, 2.7182818284590. That's an irrational number like pi, we said, right? That's the base of the natural logarithms. Doesn't really matter here. You just need to know that it's a logarithm here. What I'm going to do first is go ahead and put the 5 on the inside. Do you see with that 5 as a multiplier, I can actually move it inside. That's the natural logarithm of x to the 5th. Okay, these are the same. Plus natural logarithm of y. I guess I'll introduce parentheses. How about that 3? I'll push that inside as well. That would be the natural logarithm of z cubed, right? Okay, so we're going in the opposite direction from what we did before. Now I've got pluses all the way through. So this is just the logarithm, natural logarithm, I should say, of the product of these. You can put dots in there or you don't need to, but there it is. Okay, so you should be able to go back and forth between these two. Okay, let's do another one here. What's the base here? Base is 10, right? It's just implicit here. Okay, so I'm going to move the 4 multiplier inside the logarithm, but in order to do that, the 4 becomes what? An exponent on that fellow sitting right there. Okay? Here, the 2 becomes a power also, so it's logarithm of y squared. And then here, I could actually go negative 3 power in there, right? But what did John ask us not to use? Not to use negative exponents. He said only positive. So this is what I'm going to do. I'm going to leave this as a subtraction and move that positive 3 inside. And it looks like that. Okay? Now let's put it together. When I add these two logarithms, I would be doing what? The logarithm of the product. Okay? But then when I subtracted the logarithm from this result, I would be taking, because they all have the same base, right? Base 10. I'd be taking the logarithm of the quotient of these. So this would be the logarithm of x squared y squared over z cubed, okay? So a single logarithm, So it's logarithm of blah blah, logarithm of blah blah, okay? Let me do one last one. Here's one I threw in. Okay, so this is one of mine. What base are we dealing with here? We're dealing with base 2. Now I've got, this looks funny because I'm just sitting with a 3 out here. Okay? Well, here's what I want you to think of. This is the logarithm base 2. Of course, I'm using base 2 because it's base 2 throughout. I'm going logarithm base 2 of 2 cubed. Do you see that this is a fancy way of writing 3? Boy, that's a fancy way of writing 3. What power do I have to raise 2 to get 2 cubed? Well, the third power. Okay, do you guys see that's 3? Okay, why did I do that? So I'm making this thing look like these. Okay, I'm making it into a logarithm. Okay, logarithm base 2 of x. Bring the 4 inside. Logarithm base 2 of y to the 4th. Bring the half inside, plus logarithm base 2 of z to the 1/2 power, like that. Okay? Now they're all logarithm base 2. I can combine these into a single logarithm base 2. Logarithm base 2. Oh, maybe I should do this. What's 2 cubed? Well, that's really 8, so I'll make that into 8. Okay? Plus logarithm base 2 of x. So these two, it's really the logarithm base 2 of the product of these two. So I'll put an x there, right? Oh, I see a plus. Before I deal with this, I see a plus here on this one. So that's really logarithm base 2 of the square root of z, which is being multiplied. Well, not the logarithm, but what? It's the logarithm base 2 of the product, 8x, and the square root of z. Okay? Now, because of the minus sign right here, I've got y to the 4th coming downstairs. There it is, a single logarithm. You see where the 8 came from? Okay? See where the 8 came from? What if that had been a negative 3 instead? Then I would have had 2 to the negative 3 here. 2 to the negative 3 is 1/8, so the 8 would have come what? Down in the denominator instead. Remember, I only want positive exponents here. Okay? Anyways, there it is. Alrighty. So some problems in that sense. Now, let's come back here. There's some, I'm skipping one little subsection here in his stuff because this is actually more related to what we just did, did previously. The next subsection was actually dealing with something we'll call change of base, so we'll do that right afterwards. Anyway, 46, logarithm base b of x plus logarithm base b of y. Well, how do I compute that? Well, what you're given up here is the logarithm base b of x is 5, the logarithm base b of y is 10, and the logarithm base b of z is 7. We don't even know what b is. We don't know what x, y, or z are. All we know is these logarithms. These are all logarithms. But these are still going to be sufficient to answer, the information we have here is sufficient to give us exact answers to all these questions here. Okay? Well, this one's easy. It's the logarithm base b of x plus the logarithm base b of y. That would be what? Just reading above, that would be what? 5 plus 10 is 15. So a different question might have been to do this. What is the logarithm base b of xy? Then you would have had to do what? Break it down like that and then figure out 5 and 10 is 15. For example, that would be more akin to this problem here. Okay? Well, I got to break this down and write this as a single logarithm. Okay? So it's like these, like I was saying, write as a single logarithm, but then we know the values of the logarithms for a change. So this is going to be what? Can you break this down? It's going to be logarithm base b of x. Okay? And then I'm going to have a plus sign because this is in front, it's up top in the numerator, plus, and then the 3 is going to come out, and it'll be logarithm base b of y. Okay? And then because this is downstairs, it's going to be what? Minus, what's the power? 2 logarithm base b of z, or z if you like the British imperial term for z, z. Okay, now I know these numbers here. Let's plug them in. What's this? The logarithm base b of x. That's 5. Okay, what's the logarithm base b of y? It is 10. What's the logarithm base b of z? 7. Okay, so we have a simple calculation to do. So we can find the exact value. No calculator needed, unless you don't know your times tables. Okay, 30 minus 14. Okay. Here that would be what? 16 and 5, it looks like 21 would be the exact answer. Okay? All right. So these are some of John's problems. Let's do one Kimbolite problem here. Okay, let's break this down. Okay, this is going to be the, maybe I'll break this down a little bit more for you. This is the logarithm base b, y to the half, right? Okay, see that's times there, minus the logarithm base b of x z cubed. Okay? You agree that's true? Okay. All right, now let's break this down. This would be the logarithm base b of b plus the logarithm base b of y to the half, but I could bring the half out front, right? Logarithm base b of y. Okay, this minus sign is going to distribute between these. So this is going to be minus log base b of x minus 3, when I bring the 3 out front, log base b of z. Where's that? Okay, now put in the numbers. What's the logarithm base b of b? What power do I have to raise b to get b? First power. Okay? Even though I don't know what b is, the logarithm base b of b is something I do know. What's the logarithm base b of y? Logarithm base b of y is 10, so I'll put 10 in there. Logarithm base b of x, it's minus. Okay, 3 logarithm base b of z. Okay, let's put the numbers together. I've got 1 plus 5 minus 21. And it looks like what? Negative 20 for our answer. Okay? Assuming I did my arithmetic correctly. And I think I did. Okay? All right, so be prepared to do problems like that. Get the homework done in that section 6.5. There's one other type of question here that we're going to need. Okay? This is something called the change of base formula. Now you might notice that what on your calculators, the only logarithms you probably have, like on this one, are what, log base 10 and log base e. What if I want to compute log base 7 or log base 3 or log base 2.5? What can I do? Okay, how can I use my calculator to do that? Well, we'll show you how to do this. All your calculator really needs is a single type of logarithm, and you can get away with finding a logarithm to any base. Now here's something you need to remember for the exam. Okay, so this is the change of base formula. The logarithm base b of x is the logarithm of x divided by the logarithm of b. Here I'm using common logarithms, or it's equivalently, you actually get exactly the same number, the natural logarithm of x divided by the natural logarithm of b. In fact, this formula would be true for what? Any logarithms here. Okay? Remember, base is what? B is greater than 0, b is not equal to 1. Okay? So you can use either one of these. You're always going to get the same answer regardless of which one you use. Okay? So, choose whichever one you like. Okay? Let me give you a quick proof of why this is here. Okay? Suppose that I say the logarithm base b of x is equal to y. So I'm just giving a name to the logarithm base b of x. Okay? Now this would be equivalent, from earlier work, b to the y is equal to x, right? Because this whole thing is an exponent, right? So, and the base is b. b to the exponent gives you the value x, right? So this is saying the same thing. These are exactly the same thing. Now watch though. I'm going to take the common logarithms, that's logarithm base 10, of both sides of this and show you how it works here. You could just as well use the natural logarithm in this argument, and you would end up with this conclusion instead of this conclusion, okay? But I'll show you guys some concrete examples here in a minute. Anyways, I've got this formula. I'm going to take logarithms of both sides, base 10, okay? So that would mean what? The logarithm base 10 of x is the logarithm base 10 of b to the y. Okay, logarithm base 10 of x is what it is, so I'll just leave that alone. What can I do with this expression here? Oh yeah, I'm taking a logarithm of an exponential. I can take the exponent and put it out front as a multiplier, right? As a factor. So instead of this, I'll write y times the logarithm of b. Okay, now I'm interested in y. Solve for y in this equation. This is a number, and this is going to be a number. It's easy to solve for y. It's going to be the logarithm base 10 of x divided by the logarithm base 10 of b, or we say more simply just log x divided by log b. Okay, but what was y again? Oh yeah, y was the logarithm base b of x, which is what I was originally interested in. So I back substitute that, and I found the logarithm base b of x is the logarithm of x divided by the logarithm of b. Now you could have done exactly the same thing here. All the manipulations would have been exactly the same if I had used ln instead, or logarithm to any other base for that matter. Okay? Of course, we use log base 10 or log base e in our change of base formula because these appear on our calculators. Okay? Alrighty. So keep this in mind, though, because we're going to work a few problems here. These are going to be easy. Now here, John's trying to throw you off. Logarithm base 7 of 14. This is still in section 6.5. All this has been 6.5. No, it's not 2. You're not going 14 divided by 7. You're asking what power of 7 is 14. The answer is some weird number. Okay? Now, here's what you do. Use the change of base formula. Log of 14 divided by log of 7. Okay? Alrighty. And punch that in your calculator. Remember how to do that? Okay? Can you do it? Okay? I'll do it. Log 14. Now notice I've got to get my parentheses in there. Be careful on your calculator that you're using it right. If I forget that second set of parentheses, then I'm going to be in trouble. I'm not going to get the right answer. Logarithm base 7. Okay? Has to be exactly that. Now I'm going to round to 4 decimal places like usual. Do you see that? 1.3562. Okay? So this is approximation, but I will write equals anyway. Okay? What if I used common logarithm instead? Okay, go ln instead. Natural logarithm of 14, parentheses, divided by natural logarithm of 7. Ta-da! Exactly the same number. Okay? Does not matter which one you use. Box in your final answers. Okay? Let me make one quick comment here. 7 to the x is an increasing function, right? This is remember that logarithm base 7 is the inverse function to this? Okay? But let's go ahead and think of it. It's an increasing function. 7 to the first power is 7. 7 to the second power is 49. Now 14 is somewhere between 7 and 49, right? So that means the logarithm, which is the exponent corresponding to 7 that yields 14, it's got to be somewhere between 1 and 2. Does that make sense? And it's probably closer to 1 than it is to 2, because that's pretty much bigger than 14, isn't it? This would be rather closer. So I'm predicting it's a number between 1 and 2, but probably closer to 1. 1.3562 satisfies that condition. Okay? Again, now on this, logarithm base 9 of 36. We're not going 36 divided by 9. Okay? I'll do natural logarithm this time for no particular reason. Like we said, it does not matter. You're going to get the same answer. Okay? Let's do it. Natural logarithm of 36 divided by natural logarithm of 9. Get those parentheses in there. And I get 1 point, let's round to 4 decimal places like Kimball likes. 1.6309. Okay. Now let's try this here for a second, just as an estimate again. 9 to the first power, of course, what? That's an increasing function, 9 to the x. Okay, 9 to the first is 9. 9 to the second is 81. You look between these two values, 36 is between these two. So I'm predicting what? An exponent between 1 and 2. Ta-da. Okay, how about this one? 45 he's got. Okay, usually I picked even ones, but this is an odd one. Let's go with the common logarithm again. 0.123 divided by logarithm of 9. Okay. You're going to have to end up with a negative value up here to get a number between 0 and 1. Let's try this. Go. Okay, so I've got log 0.123 0.123 divided by log of 9. Okay. And I get to negative 0.9537 to 4 decimal places. A couple quick comments here. One reason I like to put a 0 in front, you see when I'm writing, is because it's absolutely clear. Sometimes when people are writing, you can't even see where the decimal point is. And people have a tendency to do this on their page. Okay? If I've got a 0, nobody goes 0.9 unless there's what? A decimal point there. So that reinforces the fact that there's a decimal point there. Okay? Now I want to come back here and just tell you, again, not everybody has the same calculator, but just be careful. Do you see if I did this, what I did before? If I forget my second set of parentheses here, like that, if I forget those and just go directly to division, and it goes, log 9. See how I'm off? I got the wrong answer. Okay? Why? Because it's going to, when it does this, when it looks at it, it's not going to calculate the logarithm of 0.123 at any point. It's going to do what? It's going to go logarithm 0.123 divided by the logarithm of 9. Okay? It'll take the logarithm of that quotient. It'll compute that quotient and then take the logarithm of that result. Well, that's not what we wanted. We wanted that. Okay, so be careful about that. Okay? Okay, just make sure you're getting the right answers on these things. That's why we do our homework. Okay? Look at the answers and the solutions here. Here's a quick question for you, just a challenge. Suppose the logarithm base b of a is 0.25. What is the logarithm base a of b? Notice how I switched the numbers. Okay? This was the base and this is the value. Now I switched them. This is the base and this is the value. There's a relationship between the two of these. Can you tell me what that relationship is? Okay? Give it a little thought. I may tell you at some point. Okay, on to the next section.